Hello, General Biology, and welcome to the first in the screencast series for Section 2.4 of Chapter 2, and the last section of this chapter, so you know what that means, that there's another test coming up. In this section, we're going to be talking about chemical reactions and enzymes. We already know a little bit about enzymes, that they're specialized proteins. So that's something we have under our belt already. And chemical reactions, they're going to involve changes in the bonds, and we're going to talk about some of those changes. And we're going to talk about bonds storing energy and releasing energy, and also using that energy for cellular activities that go on. So let's just jump right on in. So by definition, as we can see here, a chemical reaction is a process that changes or transforms one set of chemicals into another by changing the chemical bonds that join the atoms in the compounds. So remember when we were talking about sodium chloride, and I said to you that sodium had the property of being a metal that was explosive in water, and chlorine had the properties of being a greenish, toxic, poisonous gas. Okay, but when they joined together, it made table salt. That's a chemical reaction. And I was describing a chemical reaction to you then, and it actually changes the chemical properties of the individual atoms. And, okay, so we talked about the sodium chloride. So what that means is that there's going to be changes that happen within mass and energy. And what we're going to see in some reactions, as it says here, that mass and energy are conserved during chemical transformations, including reactions that occur in living systems. So that's one of the things. Remember, mass, when we talk about mass, it's how much we have of that substance, and that mass needs to be conserved. This is kind of a jump ahead, but when we think about the environment that we live in, it's a closed system. We don't really get new things into the system like you would think. It's all recycled. It's all recycled mass and matter. So when an organism dies and that decomposes, it goes into the soil as nutrients. And the trees and the plants pick that up through their root system, and they grow, and they increase in size and are used as a food source by other animals, even ourselves, and that material then is passed on to us. So when we have reactions occurring, that whole idea of decomposition, those are reactions that are taking place. So let's talk about the reactions specifically. So what we want to react within, an equation, because that's what we use, we write equations, but whatever things that we want to react to make something, they're going to be called the reactants. So the elements or compounds that enter into a chemical reaction, those are called the reactants. What we get from joining those two reactants together are the products. So let's go back, and I try to relate things to food whenever I can. So our reactants are our ingredients. So what elements are we going to put into this? What ingredients are we going to put into this? And what are we going to get out of it? So we were just talking about sodium chloride. So sodium is going to be one of my reactants. Chlorine is going to be another one of my reactants. And when we put it together, the product that we're going to get from that is going to be sodium chloride, NaCl. So what we're seeing is bonds are going to form, and we know that these are ionic bonds. Bonds are going to be forming between the sodium and the chlorine, and that's going to store some energy in there, and it's making this new substance, this product, table salt. Okay, so chemical reactions. There are many reactions that are happening within your body right now that is helping you to survive. I mean, everything about you being there is part of chemical reactions that are happening for your survival. So there's pictured here a reaction that is in your bloodstream that enables carbon dioxide to be removed from your body. Carbon dioxide is a toxic substance, a toxic waste substance that we need to get rid of from our body. So there is a reaction to help remove that. Cellular activity, and we're going to talk about cellular respiration in a later chapter, is a reaction that goes on that one of the waste products that is produced from that cellular respiration is carbon dioxide. So that carbon dioxide has to be removed from your system so that it doesn't kill you. Have you ever heard of a diver getting the bends, where they get too much oxygen in their bloodstream and carbon dioxide in their bloodstream, and they can't remove it, and it causes muscle cramping and all of that? Well, this is one of the things. We have to get that out of our tissues. So the carbon dioxide actually diffuses into our capillaries, because whenever you have more of something surrounding an area, it's going to diffuse in. And that carbon dioxide then will chemically react, and it will chemically react with water, which is in our blood, and it will form a compound called carbonic acid. And this carbonic acid then is going to carry that carbon dioxide until it gets into the lungs. And then once in the lungs, that CO2 is going to break away from the water and be released into the air sacs and exhaled. So water becomes kind of like a carrier for that carbon dioxide. So what you see here is a chemical reaction that is occurring. We're taking carbon dioxide and we're taking water and we're producing this carbonic acid, H2CO3. Now, notice something in this reaction that we have here. We had two hydrogens here, we have two hydrogens there. We have one carbon here, we have one carbon here. We have two oxygens here and one oxygen there, so 2 plus 1 is 3. We have 3 oxygens there. So this equation shows you that we didn't change the amount on either side of this arrow. The amount stayed the same. We just rearranged it. So a chemical reaction is rearranging your reactants to form your products. And we're changing some bonds that are going on. We now have 3 oxygen and a carbon joined with the 2 hydrogen. So we've changed the bonding that takes place. Does that make sense to you? I hope it does. Okay. So in the lungs, the reaction is reversed and produces carbon dioxide gas, which we exhale. So we've talked about that. And that's one of the things I did not mention in that last PowerPoint slide. So our carbon dioxide plus our water produces the H2CO3. Guess what? I can reverse this. I can break this H2CO3 down into water and carbon dioxide. So the reactions can happen both ways. And you're not losing anything in the reaction. You still have carbon, you still have oxygen, you still have hydrogen that's there, and the same amounts. Alright? So, reactions require energy. A reaction is just not going to happen because carbon dioxide is there and water is there. It's going to need energy. So we're going to see how energy changes affect whether a chemical reaction will occur. So how many of you like Pixie Stix? That's one of my favorite candies. Cherry. Cherry's my favorite Pixie Stick. orange. It's my second favorite pixie sticks, and I love the giant ones. Okay, pixie sticks. I want you to think of pixie sticks. When they're closed, when they're sealed, that sugar candy is stored in there, right? And that sugar candy is energy. So when we have bonds that form, bonds that are going to be forming between two electrons in the valence, there's going to be energy that's stored, just like that pixie stick, just like that candy. So what happens if I were to break that pixie stick in half? Oh no, the candy's going to fall out. I hope into my mouth, but so the candy's going to fall out. It's going to come out, it's going to be released. So when we break the bonds between two electrons, energy is going to be released. The same idea with the pixie sticks. So what that tells us is that when bonds form, or when bonds broken, that energy can be released or absorbed. And that energy, you know, if it's being released, then it's going to be used hopefully to drive other cellular reactions, or it's going to be lost. You have a body temperature normally of 98.6. That body temperature is produced by reactions that are happening in your body. If the reactions are happening normally, you're going to be at 98.6. But if there's something to cause those reactions to change, like a virus or a bacterial infection, it's going to raise your body temperature up because the reactions are going to be happening at a faster rate, trying to get rid of the invaders that happen to be in your body. So you're losing that energy in the form of heat. And that energy is also being used for the reactions to take place. So chemical reactions that release energy often occur on their own or spontaneously. And chemical reactions that absorb energy, they're not going to occur without a source of energy. So it's real easy to break something apart. It's harder to put it back together. It's going to take more energy to put it back together. So if you break a plate, probably didn't take much to break a plate, just dropped on the floor and oh, it broke. But now we've got to put all of those pieces back together again. And we're going to need some glue here and there to bind it. It's going to take some energy, some thought, some extra effort. And it's the same thing with the reactions. I'm going to throw in some terms that are not in your textbook, but I want you to get used to hearing because we're going to use them later on in a different chapter. Energy reactions that release energy, any sort of chemical reactions release energy, we're going to call those reactions exergonic. Exit, out, energy that's going to be releasing. And any reactions that absorb energy, we're going to call endergonic. And this is where in endergonic we're going to have bonds that are formed. And any time we have bonds that are formed, then that means that they're going to be storing energy. And if we store energy, that's an endergonic process. That energy is going to be stored in those bonds. Okay, we're coming to the end of this screencast. I will see you in the next screencast.